Okay, so last chapter we're going to look at is chapter 11. There's a few different topics in it, from sequences and series, binomial theorem, and then a little bit with probability and proof. So it's kind of a mixture of a lot of different stuff in this chapter. Okay, but first thing we're going to look at is what's called a sequence. So a sequence of numbers is basically just a list of numbers with a pattern to it. Okay, there's some kind of formula that's generating this list. Okay, so it's a set of numbers that have a specific order. Usually when we name a sequence, at least our book, we just use a lowercase letter. Okay, so I'm going to talk about sequence B. Okay, so this particular sequence starts out 1, and then 1/2, 1/3, 1/4. ... means it keeps going all the way up to an nth term. This is not an infinite sequence. It doesn't go on forever. If a sequence was infinite, there would be a ... at the end of it. This means that there is an end somewhere. Where does it end? At the nth term. Whatever that is. Okay. These numbers down below, that's basically how we refer to a number in the sequence. So b sub 1 is the first term in sequence B, b sub 2, second term, and so on. Okay, so any questions on how you refer to a specific term in a sequence? So, for a sequence to be uniquely determined, there has to be some kind of rule or formula that's generating those terms. Now, we're going to talk about two different types of formulas. We're going to talk about what's called explicit and recursive. Does anybody remember those? Explicit and recursive? Okay, so one type of formula is better than the other. Okay, the big idea is that one type of formula allows you to find any term you want just by knowing the position you're looking for. If you want to know the 20 millionth term, all you have to do is do something with the number 20 million. Plug it into a formula. That's easy. Another kind of formula we're going to look at says, okay, if you want to know the 100th term, you have to know the one before it. You're going to know the 99th. And if you want to know the 99th, you have to know the 98th. And to know the 98th, you have to know the 97th. So that kind of formula, not as easy to use, because to know a specific term, you have to know every single term up to that one. And that takes a lot longer. Okay, so we'll talk about what each one is called. And sometimes we'll even come up with a way to convert the kind of the cumbersome, the long, involved formula into the shorter version. We can only do it some of the time because that's a pretty hard problem, okay, in general, to convert between like the short version and the long one I have to explain. It's not easy to do. But for ours, it'll be pretty easy. So let's look at this sequence. 2, 5, 8, 11, ... Then there's another nth term, and then ... So this would represent an infinite sequence. It just keeps going. Does anybody see what the pattern is here? And there's two ways to describe the pattern. There's the way that, well, we'll go through it and you'll see what happens. Chris?
You're adding 3 to your current number to get your next term.
Okay, so to get to the next term, you're taking the previous term and you're adding 3. So if you wanted to know the 5th term, you would add 3 to the what? The 4th term. If you wanted to know the 10th term, you would add 3 to the 9th. If you wanted to know the nth term, you would add 3 to the one before that. What's the term before a sub n? Yeah.
A sub n minus 1.
Yeah. So take 3 plus the term before it. So if you want the nth term, go to the n minus 1 term. Now, what if I said to you, I want to know the 900th term? Why is this formula going to take a while to do that? Yeah.
You'd have to know the 899
Yep. You got to know every single term from the first all the way up. Okay. Not the best way to do it. So this type of formula has a name. We'll get back to it. I want to see if we can describe this a different way. What I want to do is try to describe it based on its position. So number 2 is in the first spot. And number 5 is the second number. 8 is the third number. And 11 is the fourth number. Does anybody see some kind of arithmetic you can do with the number in red to get the number in black below it? Yep.
3n minus 1.
Yeah. If you take and triple the position you're looking for and subtract 1 from it, that will give you the term. So let's try it. We want to know the number in the fourth position. Do 3 times 4 minus 1. Yep, that's 11. So now if I wanted to know the number in the 200th position, or whatever I said, it's just 200 times 3, 600 minus 1, 599. Done. So I just found the 200th number without finding every single number before it. Okay. So this type of formula, much better. Okay. All right. Any questions on describing a sequence? Now, if you're not sure, like how would I figure this out if it gets a little more complicated? It can be kind of hard to figure out. This type of sequence has a special name. When you add the same number over and over, there is a formula you can use to find this pattern. Okay, very, very simple formula. Okay, if you add the same number over and over, or you multiply by the same number over and over, like 2, 4, 8, 16, 32, if it's doubling each time, there's a simple way to get that as well. All right, so if we have a function, okay, you can kind of think of these formulas we're going to come up with as functions, but the input to the function is only integers. Okay? Think of the input as a position. You can have a number in the second position, you can have a number in the third position in the sequence. There's no number between the second and third number. There's no such thing as like the 2.5th number. It doesn't make sense. All right, so all the formulas we're going to come up with, you can think of them as a function where the domain is just positive integers. And you never plug in a decimal because you're looking at a position in a sequence. So that's always a whole number. Or a positive integer. Same idea. Technically, depending on how you do it, some people may start with the first number and call it the 0th term. So like in this sequence, you could look at this as the 0th term, first term, second term, third term. I think it's a little confusing to do it that way, so we'll start with first, second, third, fourth, like that. Any questions on that idea? And the reason the formula we come up with has to be a function is because remember the idea of a function means you plug in a number and you get one answer. Well, if you were coming up with formulas that weren't functions, that would mean you could plug in a number and get maybe 2 different answers for that term. That can't happen. Every single position has one and exactly one number in that spot. Okay, so your formula has to be a function. Okay, so if you come up with a formula that's describing an infinite sequence, then that means the domain for your formula is every single positive integer. You could find the second term, the 5th term, the millionth term, the 20 millionth term, the 2 billionth term. You can plug in any number you want into your formula as long as it's not a fraction or decimal and as long as it's positive. So kind of the flip side of that is if you don't have an infinite sequence, you have a finite sequence. Finite means it ends. Okay. So in that case, if you come up with a formula for a finite sequence, the domain is a subset of the positive integers. What does that mean? Well, it would start at 1, representing your first term, and it would go up to n. N would be a stopping point. I mean, n could be a million, could be a billion, could be a trillion, but no matter how big n is, it does stop somewhere. Right? So let's pretend, like, just try to think of the difference between infinite and finite. If I said I wanted to count the number of grains of sand on a beach, is that an infinite number or is it finite? The number of grains of sand on a beach. It's finite. I mean, it's a huge finite number. Maybe it's in, I don't know how many grains of sand are on a beach, but maybe it's in the quadrillions of grains of sand. But the thing is, it ends somewhere. There's not an infinite amount of sand on the beach. Okay. Versus if I said to you, all right, I have a pot of water on the stove, and the temperature of the water is starting at room temperature. It's like 70 degrees. And I'm going to heat it all the way to boiling. And I ask you, what temperatures will I go through? How many different temperatures? Starting at 70 all the way to boiling. Well, there's an infinite amount of temperatures you're going to go through. Because you're going to hit 82.61459.3 degrees at some point. Maybe just for like a nanosecond. It's going to be exactly that temperature. But it will be that temperature at exactly some point. In fact, even if you just heat water from 70 degrees to 71 degrees, you go through an infinite amount of temperatures, just from 70 to 71. Right? So that's infinite versus finite. Any questions on that idea? So we're going to work with both kinds of sequences. All right. So this one basically just giving you a formula, and all they want you to do is list the first 3 terms and the 15th term. So remember, n is the position. So if you want the nth term, it's n squared minus 1 over n. Now, that would be a little more complicated formula to try to come up with by hand. Right? When patterns start involving squaring numbers and adding and subtracting and dividing all in the same formula, it's getting a little hard to figure out by hand. Right? So Kaya, if I want to know the first term, what would I plug in for n?
1.
Yeah. And if I do that, I'm going to get 1 squared, which is how much?
1.
1. Minus 1 divided by 1. Right? So Gabe, if I fill in 1 for n, what do I get?
1. 0.
0. Yep. So this particular sequence, the first term is 0. Emily, to get the second term, what would I plug in?
2.
2. And what's 2 squared?
4.
So 4 minus 1 divided by 2. So if I do that up, Chris, you can just leave it as a fraction. What would I get?
3 seconds.
3, yep. 3 seconds, 3 halves. Right. And now let's do the third term. So 3 squared is 9 minus 1 divided by 3. So 8 thirds. Right. And Nate, what would be the last number I'd plug in for n?
Like the 15th.
Yep, the 15th one. Now, do I have to find the 4th, the 5th, the 6th, the 7th, the 8th, the 9th? No, I can just jump right to the 15th because I've got the kind of formula that doesn't have this in it. If your formula says do something to the term before you get the next one, that's going to be a problem. It's going to take a long time. All right, so we plug in 15. What is 15 squared?
225.
So 225 minus 1 divided by 15. So that's 224 over 15. Now, if you look at it, you can kind of start to see a pattern. 3 divided by 2 is 1.5. 8 divided by 3 is what? 2 2/3. About 2.7. 224 divided by 15 is roughly 14.93. What's happening to the terms in this sequence? As the position gets higher and higher, does anybody see what the pattern is? There's a relationship between the term you get and its position in the sequence. Let's do one more. Let's do the 20th term. What's 20 squared? 400 minus 1? So 399 over 20. So if we divide that out, we get 19.95. Actually, that's exact. So anybody see the relationship now between the term and its position? Yep, Chris?
So like the nth term to like 20, going from the 20th term, the number you get is almost 20, but not quite, and as n increases, you get closer and closer to your n, but not quite. So like n equals 2 is 1.5, which is almost 2.
Yep.
But n equals 20 is 19.95, which is closer to 20 than 1.5 is.
Yeah. So what's happening here is as the terms go further and further in the sequence, the actual term is getting closer and closer to its position number. Right? So the 20th term is just a little less than 20. And that's because, look at your formula. If you have a number and you square it, say like a huge number, like 1,000,000. If you square 1,000,000, or you square 1,000,000 and subtract 1, is there that big of a difference between those two numbers? Not really. I mean, compare like 1,000,000 to 999,999. It's basically the same number. So when n starts to get really big, your formula basically turns into that, okay, as n approaches infinity. Okay? When n is small, no, that 1 makes a huge difference. Compare the number 4 to the number 3. That, if you look at it, that's a pretty big difference. It's only 1 unit away, but think about that as like, the number 4 versus the number 3. 3 is only 75% of the number 4. But here, 19.95, that's almost 100% of that number. It's very, very, very close to it. Okay? So if you take n squared and divide by n, just use your rules for exponents, that's basically what happens. As n approaches infinity, your formula turns into just n. That minus 1 doesn't make a big difference. All right. So if I gave you these fractions, that would probably be a very hard formula to figure out. I don't think we'd be able to do that by hand yet. But you should be able to list out the terms and then describe the pattern you see. Okay, let's try this one. Now, first thing I want to look at is just this. Remember, n has to be an integer. It can't be a fraction, can't be a decimal. So when you do -1 to the n, what do you get? Chris?
You only either get a positive or negative.
Can you tell me when you would get what?
If you have, if your n is an odd number, you get -1.
Right. So that should tell you that each term in this sequence is going to alternate, positive, negative. That's part of it. Okay? This 2 is also going to cause every term to double. So the terms in this sequence are going to double and alternate positive, negative. Okay, so let's find the first term. So we have negative 1 to the 1 times 2 to the 1. Right, so Kathleen, if I do that, what's negative 1 to the first? And then 2 to the first? And negative 1 times 2? Negative 2. So there's your first term in the sequence. Natalie, how about second term? What's negative 1 squared? Positive 1. And 2 squared? And positive 1 times positive 4? 4. So once we see the pattern, we can just kind of keep going. The third one would be negative 8. The fourth one would be 16, negative 32, positive 64, and so on. And now let's do the fifth term. 15th term, sorry. So we got negative 1 to the 15th. What's that going to be? Yep.
Negative 1.
Negative 1. That one's easy to do. 2 to the 15th. This is going to be a pretty big number. Probably not in the millions. Probably still in the thousands, but pretty big. So let's do negative 1 times 2 to the 15th. So 2 to the 15th. So 32,768, and we're going to make it negative. Okay, so this gets into what you would have studied in Algebra 1. That's like an exponential pattern. Okay, exponential means you're doubling each time or tripling. So the numbers get really big really, really fast. Okay? Versus a pattern like the one we had back here where we just add 3 each time. They don't really get that big that fast. This is more of a linear pattern. Okay, so that's why you can describe this as a formula that looks kind of like a line. You've got a slope of 3 and a y-intercept of negative 1. Okay. To describe something like this pattern, not a line. It's going to be a curve. Now, this would be kind of weird to draw because you're alternating positive, negative. But let's say it was just doubling each time. 2, 4, 8, 16. Your graph would look like this. It would be an exponential curve. Because it alternates positive, negative, you can't draw it. If you try typing this in on the calculator, you won't get anything. It won't work. So, any questions on finding those terms? So if we want to graph it, okay, the way you could graph a sequence, it's basically just like graphing a function, except technically you would just have dots. Okay? If you were to graph a real exponential, like here's an exponential, f of x equals 2 to the x, it would look like this on your calculator. It would be connected. Now, if we limit the domain to integers, what would it look like? It would look more like points. First term, second term, third term, fourth term, and so on. Okay. So the graph of a sequence would look just like the graph of your function, except technically you wouldn't connect the dots because there's nothing in between the second and the third term. It would just be empty space. So the graph of a sequence looks kind of like that. Just only graph the positive integers, just those dots. Any questions on that idea? Yeah.
Do you think it would be like different if you use a different number system, like other than decimal? Like the dots would connect, like if you use like binary, like octal or like anything else?
Well, we're really, when we think of a sequence, we're thinking of each number has its own specific spot. So you've got a first spot, you've got a second spot. There's nothing ever in between the first and the second spot. So what you put in the sequence, whether you put letters or numbers, even if your numbers were a different number system, there'd still be nothing in between the first and the second spot. So like even if you call this triangle, and you call this square, and then you call this pentagon, I'm basically just, my pattern is I'm just adding a side each time. I'm not even using numbers, but no matter what you use, there's nothing between square and triangle. So I don't think it would ever connect, because sequences are discrete.
Yeah.
They're not really continuous. You know, kind of like runners in a race. You know, somebody might get 3rd place, somebody gets 4th place. Who got 3.5th place? Nobody. It just doesn't exist. Does that make sense?
Like, there's nothing in between.
There's nothing between them. And it's like if I was counting how many desks are in this room. Maybe I count them and there's 27 desks, or maybe there's 28 desks. But there's not 27 and a half desks. Like, I either have a desk or I don't have the desk in here. There's nothing in between that. Yeah. So yeah, the pattern when you graph a sequence would never connect. Now the dots could look closer or further apart. It depends on the formula. But there still would always be some type of small gap between them. All right, so let's try to graph this sequence. Okay, so graphing the sequence, just like graphing a regular function, just remember, n can only be integers, okay, positive integers. So let's just make a table and pick some values. All right, we usually start with 1. Okay, that's our first value. Now, this is the same formula we just did. N squared minus 1 over n. So we already know what some of these come out to. 0, 3 halves, 8 thirds. So 0, 3 halves, 8 thirds. I just put in 4 and 5 because I got a little space, and they're gonna fit on the graph. Now, remember what it should look like. This formula basically turns into that as n gets bigger and bigger. So if you were to graph y equals a number, it's basically like y equals x. It's going to look like a line with a slope of 1 and a y-intercept of 0. Now, technically here the y-intercept doesn't make sense. The y-intercept would be the 0th term. We don't really talk about having a 0th term in this kind of stuff. We'll start with the first term. So 1, 0. 2, we're going to be at 1.5. 3 8 thirds, that's what? 2 1/3. 3, 2, oh, whoops, that's 1.5. 2 1/3, roughly.
Wouldn't the 0 be down? On the
1 0, thank you, yeah. 1 0, because it should look like a straight, pretty much a straight line. When we do 4, that's going to be 15 fourths, right? So that's what? 3.75? All right, so 4, 3.75. 1, 2, 3.75. So it's going to be getting closer and closer to that horizontal line above it, but that dot is never going to reach it. We'll do one more. When we do 5, we are at 24 fifths. Okay, so that's going to be what, 4.8, I think? Yep, 4.8. So 5, 1, 2, 3, 4.8. So just getting closer and closer. Now, should I connect the dots? No, don't connect them, because there's nothing in between the second number and the third number. So that's how you graph a sequence. Okay, we're not really interested in graphing sequences that much. We mostly want to find the formula. But if you wanted to graph, that's how you do it. Any questions on that? So, the kind of formulas that we've been looking at are what we call explicit formulas. That's an explicit formula. That's the same explicit formula. That's an explicit formula. And the one that you guys gave me, this one is explicit. The top one you gave me is not. We'll come back to that. So the advantage of an explicit formula is you can find any term you want right away, and you don't need to know the one before it. If you have the kind of formula where to find the next term, you have to know the one before it, that's called recursive. Okay, that's a recursive formula. Okay, so the way a recursive formula works is they will start you off with the first term, or sometimes even the first couple. And then if you want to know another term, it's always defined using the one that came before it. So recursive formula is kind of a pain to use by hand, because if you had to find like the 200th term, not only does it take a long time, but if you're doing it by hand, when you make one mistake getting to the 200th term, then the whole thing is messed up. Okay, so explicit, you can find what you want right away. Recursive, you got to find everything up to the one that you're looking for. Okay, and recursion is a pretty fancy thing. They use that a lot. There's a whole type of computer programming that involves recursion. And it's hard because recursion is almost like putting two mirrors in front of each other and then looking, and then you kind of see like that infinite image. Well, recursion is kind of like that. It's like you keep seeing this process repeat over and over and over. Unlike with two mirrors, that's actually infinite. Like the reflections go on forever. With the recursion, it stops somewhere. So this is a pretty famous problem. Has anyone ever seen this? The towers of Hanoi? You have like discs that look like this, and they're stacked on different poles. And you have to move all the discs from one pole to the other pole, but you can never put a bigger disc on top of a smaller one. You can only stack smaller ones on top of a bigger one. And the goal is to get this pile of discs over to that pole. And you can use the one in the middle to help you. And it turns out it's a recursive programming problem. And you can do it for, you could have like 30 discs, getting smaller each time. All right. But if you don't know recursion, it's a very, very hard problem to solve explicitly. You really can't do it. Okay, so here's an example of a recursive sequence. They've told me the first term is 2, and then they've said, okay, to get a particular term, take 3 plus the term that came before it. That's what this notation always means. A sub n minus 1 is the term before the one you're looking for. And that's why they have to tell you the first term, because imagine they didn't tell you the first term. So you'd say, all right, to get the first term, add 3 to the 0th term. Well, the 0th term doesn't exist. So with recursion, you have to start somewhere. So, okay, start here. What would the next term be? 5. And the term after that? 8. So, I mean, not that bad. Okay. But if you had to do this for, say, thousands of numbers, and the steps were a little more complicated than just adding 3, starts to become kind of a pain really quick. All right, so here's a recursive formula. I want to find the first 4 terms and the 8th term of this. So the first term is 2. And if you were just looking at this, how would you explain to somebody how to get the next term if they didn't understand like this fancy notation? Just kind of simplify what you do each time.
Add 4.
Add 4 to what? Yeah, just add 4 to the one that came before it. Right? So let's find the first 4 terms. And then the 8th term. Okay. So what's the first term? 2. How do you know that? It's given. Yeah. They got to give you that. Okay. Now, how about the second term? 6. Just add 4. Add 4, add 4. Now, technically, they didn't ask for the 5th, the 6th, and the 7th term, but to get to the 8th term, if the rule is to add 4 each time, then we kind of have to go through it, unless we look at how many times we added 4 and just multiply. So we can kind of come up with some shortcuts, but this isn't that bad. So my 5th term would be how much? 18, 6th term? 7th? And 8th. So what they really wanted was that and that. Okay. Any questions on that? Okay. All right, so now we're going to take a look at a recursive formula and see if we can turn it into explicit. The easiest way to do this is going to be to just make a little table, look at the pattern, see if we can figure it out. In general, it's very hard to turn a recursive formula into an explicit, especially when the formulas get more complicated. I mean, this is just plus 5 each time. That's not bad. But this can become an extremely hard thing to do. All right. So let's list out the first few terms so we can kind of get a pattern going. My first term is 3. What's my second term? 8. And what's my third term? 13. So I'm trying to figure out, we could do one more if you want, just to have one more. That'd be 18. I'm trying to figure out something I can do with this number to get that number. Anybody see what you can do with the position number to get the term? Multiply what? All right, let's try it. 1 times 3, does that give me what I want here? Okay. 2 times 3, does that give me what I want here? No. So sometimes you find kind of a rule that might work for the first one. Sometimes it even works for the first 2, but then it starts to fall apart. So it's not times 3. Anyone else? Yep, Kathleen?
5 and minus 2.
Well, can you just say it one more time?
5 and minus 2.
Yep, if you multiply the position you want to know by 5 and minus 2, there's your pattern. 3 times 5 is 15, minus 2 is 13. 4 times 5 is 20, minus 2 is 18. So yep, that's the formula. 5n minus 2. Now, we haven't really learned the shortcut yet, but if you know you're adding 5 each time, that 5 is going to be part of the formula. And then the minus 2, well, that we'll learn how to get it, but I'm guessing whoever got it just kind of looked at it and just figured the pattern out because they're good at seeing patterns. Any questions on that one? So let's look at this pattern. So this is a very famous recursive sequence. Most people, if you say the name Fibonacci Sequence, they've heard the name. Maybe they don't know exactly what it is, but they've heard of it. And the Fibonacci sequence is a recursive sequence that uses the 2 previous terms. Right. So this is how you get the nth term. Now, if I showed that to someone in Algebra 1, they'd have no idea what all this means. But it's actually not that complicated of a pattern. How would you explain what this is saying to do? To get the term you want, do this. Yep.
To get the term that you are looking for, you add together the two previous terms.
Yeah, that's it. So to get the term you're looking for, just take the previous two and add them together. That's why if you're going to write a recursive formula that depends on the previous two terms, I have to start you off with two terms. If your formula depended on the previous three, I'd have to start you off with three. Okay. So we've got 1, 1. That's the first two. What's my next term after that? 2, and then 3, 5. I don't know how many they wanted. 1, 2, 3, 4, 5, 6. Yeah, we're done. Now, that is an extremely difficult one to get as an explicit formula. So like if I said to you, tell me the 595th Fibonacci number. There are ways to do it. You don't want to have to list out 594 to get to the 595th. It's going to take a while. But it's way beyond what we're going to do. Okay, so that's all I'm really going to say about it. And I honestly don't remember how to do it. It was pretty complicated. But any questions on that? Okay, so that's a pretty famous Fibonacci sequence. Now, a Fibonacci sequence, it's actually part of a bigger group of things called a Lucas sequence. Anytime you start with two numbers and add them together to get the next one, that's called a Lucas sequence. If you start with the numbers 1 and 1, it's a particular Lucas sequence called the Fibonacci sequence. Okay. All right, so I want to look at this diagram for a second. And we're going to look at Pascal's triangle more later on. But that's what this diagram is. It's Pascal's triangle, where there's ones going down each of the sides of the pyramid, and then each number is the sum of the two above it. So to get 8, you add 1 and 7. To get 28, you add 7 and 21. Okay, so each number is the sum of the two above it. Now, kind of a weird thing, but the Fibonacci numbers are hidden in that triangle. And the way they're hidden is right on the diagonals. If you draw a line right through the diagonals like that, watch what happens. The first diagonal, the top one, I just want to count it if it goes through the middle of the hexagon. Okay? It goes through the number 1. Okay. Now, look at, actually, you know what? I think I have it 1 off. There we go. Goes through 1. Look at the second diagonal. What number does it go through?
1.
Just 1, right through the middle. Now, the third diagonal goes through what numbers?
1.
1 and 1, which adds up to what? 2. Now, this diagonal goes through a 1 and a 2, which adds up to 3. We'll do one more. The next one goes through a 1, a 3, and a 1, which adds up to how much? 5. If you keep going and adding up the numbers on the diagonal where the red line goes right through the middle of the hexagon, you get the Fibonacci sequence. So there's like, I don't even know all the stuff about this triangle, but there's tons and tons and tons of patterns in this triangle. Lots of stuff. It's kind of exciting. No. Okay. So it also tells you stuff about probability. Like if you said to me, there are 10 people standing here, and I want to know how many ways can I pick 3 out of 10 people. Like I could pick persons A, B, and C, or I could pick persons B, E, and F. Okay? How many different ways can I pick 3 people out of 10? This triangle will tell you that if you go to the right row and the right column. Like row 10, column 3 would tell you exactly how many ways there are to do that. Okay? A little weird because you start with row 0, you don't start with row 1, but we're going to talk more about this triangle later. But I just wanted to show you that the Fibonacci numbers are hidden kind of in that triangle. And kind of another weird thing, if I remember it correctly, somebody let's just name some prime numbers. What's the smallest prime number you can have? Yeah?
2, 1.
No. 2. Smallest prime number is 2. It's the only even prime number that exists. What's the next prime number? 3. And the next one? 5 and 7. We'll do one more. 11. If you look at a prime row, all the numbers in that row are multiples of that number. So look at row 5. This is row 5. That's a prime row because it's 5, and every number in that row is a multiple of 5. Look at row 7. 7 is a prime number. Every number in row 7 is a multiple of 7. That doesn't work for every row. Like you say, oh, well, look at row 6. No, not every number in row 6 is a multiple of 6. Okay. But any number that's a prime row, like, what's this, 4, 5, 6, 7, 8, 9, 10, 11, every number here is a multiple of 11. And every number here should be a multiple of 13. So it's just kind of another weird pattern that pops up in this triangle. Okay. So all kinds of stuff. All right, so last two things we'll talk about are two special sequences that have names. You've already seen both of them today. Arithmetic and Geometric. When you see the word sequence or progression, it means the same thing. So an arithmetic sequence, kind of the big idea, it's a sequence where you add to get to the next number. So there's some number, which I'm calling D, that you can add to the term before and get the next term. So let's take a look at this, 2. And I want to plus 5 each time. So the next number would be 7, then 12, 17, 22, and we keep going. So D is the number that I added each time. I added 5. Well, watch what happens. What's 22 minus 17? 5. What's 17 minus 12? 5. 12 minus 7? And 7 minus 2 is 5. When you subtract two numbers, what is that called? The answer. Yep. Difference. That's why we use the letter D. So D is the common difference of the sequence when you subtract a term and the one that came before it. So as long as you know two things, if you can tell me what the common difference is, and you can tell me the first term that you started with, you can come up with a formula. Very easy. So here is the explicit formula for an arithmetic sequence. So now you don't have to guess. It's like you don't have to say, okay, you multiply it by 4 and then subtract 3 each time. You don't have to do that. If you add the same number each time, here's your formula. A sub n equals the first term plus n minus 1 times d. And there's two things you have to fill in. Fill in the first term, fill in the common difference. And remember, n has to be a positive integer. Okay, you don't fill in decimals, don't fill in negatives. So let's go back to one where we just kind of had to guess what the formula was and see if this gives us the same result. Okay, so just remember, first term plus n minus 1 times d. So we had one right here. Okay, here's the first term. So a sub 1 is 3. And the common difference was 5. 18 minus 13 is 5. 13 minus 8 is 5. So if I had to come up with a formula for this without trying to guess what it was, All we have to do, it's the first term plus n minus 1 times d. There's your formula. Now, it doesn't look the same as that, but that's because it's not FOILed out. Just distribute it out. You get 3 plus 5n minus 5, and then combine like terms. 5n minus 2. So it gives you a very mechanical way to find the formula without trying to guess. If it's arithmetic. Not every single problem is arithmetic. So let's try it on this one. Let's find those two things. What would be the... Oh, I got to tell you something. I haven't told you enough information. If that's all you had on a test, you can't answer that question. They've given you an explicit formula, and they haven't told you where to start. So I got to give you a starting point. Okay. What do you want the starting point to be? Pick anything you want. Any number. Your favorite number.
2.
Number you hate the most, even. Yeah, 2. Nate, what's your favorite number?
Probably like, I don't know, that's a hard question.
Yeah. You know what number I like? I like 12. Because it's divisible by 2, 3, 4, 6. You can't go wrong, right? 12. It's a nice number. Like the number like 7. I don't really like 7. 7 days in a week. Alright, so we got to know the first term and we got to know D. So what's the first term in the sequence? Why? Yeah, well I did. Somebody did. So it was given. And what would be the common difference here? 3. If you made a list of terms, 2, 5, 8, wrote them out, you're adding 3 each time. So subtracting one term from the one before it, you'd get 3. So what would be my explicit formula that I would write here? You don't have to FOIL it yet. Just tell me what I would write down.
2 plus n minus 1 times 3.
Times 3. Yeah. And now you do want to do that out. So you're going to get 3n minus 1. That's your pattern. Right. 3n minus 3, but then a minus 3 plus 2 is a minus 1. Okay, the nice thing about this, you can check it. Just list out a few terms and then try your formula, see if it works. Any questions on that? Alright, so let's finish up with the formula for a geometric progression. So, geometric progression, a little different. This is when you multiply each time to get the next term. Okay, so recursively, your formula looks like this. To get a term, take the one before it and multiply by a number, whatever r is. So an example would be like 3, 6, 12, 24, 48. That sequence I just wrote is going to fit into the formula I'm about to show you. If you look at 48 divided by 24, what do you get? 2. And if you take any term and divide by the one before it, you will get 2. When you divide two numbers, that's a ratio. So R here is called the common ratio. And it's found by taking a term and dividing by the one before it. That's what I just said. Take a term, divide by the one before it. That's your common ratio. So, the explicit formula for a geometric sequence, kind of like an arithmetic, relies on 2 things. What's the first term? You got to know that. And you've got to know what your common ratio is. So a sub n equals a sub 1 r to the n minus 1. And we'll finish up by just trying it on that example. Now, what's a little tricky in example 9 is they didn't give you the first term, but you should be able to kind of see a pattern there and figure it out. If they didn't say geometric, you wouldn't know. There's not enough numbers here to know. But if you know it's geometric, then you know they multiply it by something each time. So, you multiplied by -2 to get to the next term. So look at the common ratio. 12 divided by -6. That's how I figured it out, is -2. So, what would have to go in your first term? How much? 3, yep. Because -6 divided by 3 is -2. Now you've got your first term. And what's the common ratio? What do you multiply by each time? -2. So your formula, a sub n equals a sub 1 times r to the n minus 1. Let's just try it for the third term. 3 minus 1 is 2. -2 squared is 4. 4 times 3. Perfect. And that's your formula for a geometric progression. And so we skipped like one example of the notes we didn't do, but I think you guys will be okay. We'll go over the homework tomorrow, and that'll cover anything we missed. Okay, so homework, it's on 589. It's 1 through 7 odd, 9 to 13 odd, 14 that's the only even, and then 17 to 27 odd, and 31.